A very good afternoon to all the participants and our distinguished speaker. I am Dr. Bharti Patru, Technical Officer, TM Facility in Charge at SAFE CRNTS IIT Bombay. I welcome you all for today's talk on basics of transmission electron microscopy and analytical electron microscopy. The talk will be presented by Dr. Tetsuo Uikawa. Before we proceed, I would request our head of the department, Professor Suparna Mukherjee, to give an overview of SAFE CRNTS department. Over to you, madam.
Thank you, Bharti. Thank you. So I would briefly like to introduce to you SAIF and CRNTS, and I welcome all who have assembled here for the webinar and also our speaker for the webinar today. So SAIF and CRNTS actually started as separate departments. In fact, SAIF is a DST-supported center that existed since 1976 at IIT Bombay. And CRNTS IIT Bombay was started as an academic unit in 2005, and the two were merged in 2008. And currently, we have a large number of sophisticated instruments here in SAIF CRNTS IIT Bombay. And we also have PhD students. Currently, there are around 83 PhD students who are guided by faculty members across the institute. And we handle samples from all over India. And these are some of the numbers that are indicated here for the financial year 2021-22. And we have various facilities at SAIF, electron microscopy facilities like FEG-TEM 300 kV, then FEG-SEM, then dual beam, and under mass spectroscopy facilities, we have GCMS, HR, LCMS, QTROP, and Orbitrap. And we also have various other instruments like CHNSO analyzer, ESR, FTIR, NMR, X-ray scattering, and profilometer. And also we have a suite of thermal instruments like the TGA and DSC and DMA. The last one is not yet installed, but it will be available shortly. These are some of the facilities we have in CRNTS. They are institute central facilities, ICP-AES, laser Raman spectroscopy, then environmental scanning electron microscope and field emission gun microscope 200 kV. And we also have 2D GC with MS detector and UV spectrophotometer. And so from here, you see that we get a large number of samples from Maharashtra itself, but we also get from all over India, which is quite remarkable. And these are our staff members of SAIF and CRNTS who keeps the analytical instruments in good functional condition and also analyzes the samples together with also help of student TAs who volunteer their services in SAIF CRNTS. We also get a large number of visitors, as you can see, from different places from time to time. And we hold webinars from time to time, and these are also uploaded in the YouTube channel of SAIF IIT Bombay. And we also have a LinkedIn page. I welcome you all to follow us on LinkedIn. And now I welcome Dr. Tetsuo Okiyama to make the presentation on basics of TEM and analytical electron microscopy. We are eagerly waiting for the talk. So Bharti, I hand over to you now. Thank you.
Thank you, Madam, for presenting the information about the facilities at SAFE CRNTS IIT Bombay. I'm Aradhna Nodial, Senior Technical Superintendent. I will now introduce today's speaker, Dr. Tetsuo Uekawa, who is currently a Senior Product Manager for TEM at Geol Asia Private Limited. Dr. Tetsuo Oikawa is an internationally renowned expert in the field of electron microscopy with a career span of more than 4 decades in research and management experience. He has vast knowledge in the field of electron microscopy, electron energy loss spectroscopy, analytical electron microscopy, and image science. He had been director to European Application Geol Europe Group for the period 2007 to 2011. He was also invited professor at the University of Paris for 8 years during 2005 to 2013. Dr. Oikawa has received his doctorate degree from Kogakuin University in the field of electron wave optics. He has given multiple talks and seminars all around the world and has 3 papers published in the Nature journal. We are sure that this talk will be useful to you to understand transmission electron microscopy as well as associated analytical techniques like EDS, STEM, and EELS for your research purpose. An important note, queries related to today's talk should be posted in the question and answer box only. We will be floating the feedback form shortly. Kindly fill the same. So let us begin today's talk. Over to you, Dr. Tetsuo Oikawa.
Okay. Thank you very much, ladies and gentlemen, and also many thanks for organizer for arranging excellent webinar today. And thank you very much for kind introduction. Okay. So my name is Oikawa, and today I'm very happy, and it is very great honor for me to give my presentation in IIT Bombay. Okay, thank you very much. Okay, today's subject as entitled Basic of TEM and Analytical Electron Microscopy. In this talk, I'd like to introduce the basic principle of TEM and diffraction and analytical electron microscope. Okay, as today's subject as contents is listed as like this. First half, I'd like to introduce the conventional transmission microscope and a high resolution electron microscope. Just one, please. Okay, and introduce the electron diffraction. Okay, and latter half, I'd like to introduce the analytical electron microscopy and mainly for the STEM operation mode, and also analytical instrument of EDS and electron energy loss spectroscopy. Now I'd like to move to start the introduction of transmission electron microscope. Okay. As in the transmission microscope is invented in 1931. In that generation, a young engineer of Dr. Ruska invented this microscope, but this left hand is a experimental instrument, first prototype transmission electron microscope, and after that, electron microscope technology was developed, and also many commercial transmission microscope is distributed, and electron microscope give a lot of contribution to human society. As owing to this human society contribution to the human society, Nobel Prize was given to 1986, like this. Okay. So transmission microscope is now very important tool in both in material science and also biological life science field. Okay, so in the electron microscope, instead of the visible light of optical light, electron is applied. But as you know, electron is a charged particle. Why the electron gives a wave in the microscope? This is just a simple understanding as like this. Electron is accelerated in the vacuum condition as electron negatively charged. The electron starts running on high speed toward to the anode, the applied voltage. in this electron movement is equivalent to generation of electron wave. Here, this idea is developed by the Professor Dobroi, the wave named as the Dobroi wave or material wave. Okay. In this situation, electron does not change the wave. Wave is generated, but wave and the electron both simultaneously exist. Even the electron wave generated, but electron also can arrive into the anode like this. Momentum also kept. In electron microscopy, we can apply this electron wave as a phase contrast or electron diffraction, and simultaneously in analytical microscope, this electron momentum can be detected by the energy loss spectroscopy or X-ray analysis. So both wave and momentum phenomena is very important and convenient in the electron microscope. As the electron wave has wavelengths same as visible light, as the visible light has wavelengths 50 to 700 nanometer order depending on the color, but electron wave is very short, also depending on the accelerating voltage. In the case of 100 kV accelerating voltage, wavelength is 0.0073 and 0.0025 at the 200 kV. Owing to this small wavelengths, electron microscope very high resolution imaging. As electron can be focused by electromagnetic lens, as electron is running in the field of magnetics due to the Lorentz force, according to the Fleming's left-hand law, electron direction trajectory is bended as like this. Then, as electromagnetic lens made of ring shape of the electromagnetic pole piece like this, then electromagnetic field is generated from upper to lower electron trajectory crossing this field of magnet. Then, owing to this magnetic flux, lens direction is changing and focusing after the lens system. This magnetic lens focusing phenomena is equivalent to the optical convex lens in geometrical optics system. So we can consider this magnetic lens for electron trajectory is exactly equivalent to the convex lens for optical visible light. It's very easy to understanding. As you are very familiar to optical microscope as like this, lens made of glass and a visible light is illuminated, but the magnification almost limited as a 2000 times magnification, and resolution is about the 0.2 micrometer order. This is due to the wavelengths of visible light. Then, as comparing the phenomena of the electron and the visible light, left hand is light microscope, right hand is electron microscope. Principle is quite similar. At the source of visible light is a lamp as like this. Light is collected by the condenser lens and illuminated the specimen. Specimen is also very thin. Transmitted image was magnified, objective lens, and also projector lens magnified. Final image is projected on the screen as visual image. As a similar way, but in the electron microscope, source is not a light, but electron. So here we call the electron gun, but recently we call the electron source, okay? Because the gun is a little bit dangerous tool, so bad impression in the human society. Then we now recently electron source is installed here. And electron is generated from the source. Simultaneously, electron wave is generated, condenser lens, but made of magnetic lens, focusing the beam on the specimen, and transmitted image by electron on the specimen. Also, specimen should be very thin as electron can be transmitted. Thickness approximately less than 200 or 300 nanometer order. Thinner is better. Transmitted electron image can be focused and magnified first stage of objective lens, also made magnetic lens, and final stage projector lens magnify the image on the screen. But this image is electron waves. It is not visible. Then image intensity is transferred by fluorescent screen to visible light. We only observe the visible light after transfer the fluorescent screen like this. So the image forming is very similar as optical microscope. Only the difference is electron wave and also magnetic lens is applied. Okay, appearance of the electron microscope is right hand, like this. Okay, the machine is very big as comparing the optical microscope. Then microscope column inside there are the many magnetic lens. On top of the column is the electron source, and inside of that column is kept in high vacuum condition in order to be running the electron in the column like this. We can observe the binocular on the screen, transfer the image to visible light by the fluorescent screen, and both side operation console and also computer control system, we can make a remote operation by the client PC as like this. Final image is acquired by the digital time CMOS camera or CCD camera recently. Okay. As approximately magnification, maximum magnification is 1.5 million times, very high magnification possible, and resolution approximately 0.2 nanometer order, 2 angstrom. And recently, owing to the aberration collector microscope, we can obtain picometer order resolution. So as like this, illumination by electron wave, light of electron, and focusing by lens, electromagnetic lens, as like this. Okay, so the microscope, electron microscope information, it offers many kinds of information from the specimen. First one, morphological observation possible. Same as optical microscope, we can measure the size and the shape of the target object. And also, we can make a structure analysis. We can measure the inside structure, such as the atomic arrangement of the crystal, and we can make a crystallography analysis by electron diffraction and also high resolution imaging. And also, elemental analysis possible in the specimen is local area. Okay. As resolution is almost angstrom order and less than the nanometer order, in this small area, we can measure the elemental concentration on the specimen. And also, owing to the higher coherency of electron wave, we can measure the potential of electron, such as the volume potential or electrostatic potential or magnetic flux, magnetic potential if sample is a magnetic sample. We can measure this kind of potential by coherent electron waves. Today, I can introduce some practical application data while in the explanation in the basic technique. Okay, as starting point, this is the image formation of the transmission microscope. There are the two kinds of image formation. Left hand is the scattering absorption contrast. In this illustrate, the magnetic lens is illustrated as optical convex lens like this because focusing function is equivalent to the glass lens. So as for easy understanding, illustrate is an optical convex lens. As electron irradiated the sample, very thin specimen. Okay. And some of the electron passing through the vacuum area. Intensity can be arrived the image plane as original higher intensity. This hatched intensity corresponding the intensity of electron higher intensity without any absorption on the specimen. But some of the electron passing through thicker element, some of the electron is absorbed. Electron intensity reduced in the image plane like this. As like this, electron absorption or scattering intensity is modulated due to the thickness. We call this is the scattering and absorption contrast. And also simultaneously, if specimen has a some of the crystalline, the crystal generate diffraction as like this. Then combination with a small diameter of objective aperture, scattered electron is cut on the path like this. Then electron cannot reach to the image plane. In the image plane, this electron as if scattered inside of the structure. Then this contrast is called the diffraction contrast. As a combination with a small diameter of objective aperture, we can clearly observe scattering, absorption, and diffraction contrast like this. This intensity is amplitude of electron. This image formation is quite similar as optical light microscope. On the other hand, light one is a phase contrast. Okay, as a sample as the crystalline, electron generate a scattering diffraction condition. As applying the bigger objective aperture, scattered electron is accepted for image formation, as the backfocal plane transmitted the electron and the scattered electron as generating the interference fringes due to the scattered path different phase difference generated. The final image generated by the coherence and the interference fringe due to the phase contrast difference. This image is called the phase contrast. Okay? In the high resolution imaging, this phase contrast is very important. I'd like to explain in detail later in high resolution imaging. Okay, as this is a diagram of image forming lens system. As conventional imaging mode, here is the objective lens, specimen installed here, just front of the objective lens. Magnified image is also magnified intermediate lens. Here is the three stage of intermediate lens, magnify, 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 and finally additional projector lens, high magnification magnified. So each projector lens has a 10 times magnification, and objective lens has about a 50 times magnification. Projector lens have about a 200 times magnification. Finally, we can easily obtain 1 million times magnification. And also, owing to the small wavelengths, resolution very high, we can observe the atomic imaging, atomic resolution imaging, so high magnification condition. Okay. Sometimes also we need a very low magnification, same as the optical microscope. In this condition, objective lens turn off. Instead of objective lens, long focal length of objective mirror lens is turned off. Due to the long focal length, magnification is very low, and low magnification of intermediate lenses to combine. Finally, we can obtain the lowest magnification, about 20 or 50 times magnification. This is similar as the optical microscope magnification. As like this, changing the focal length of magnetic lens by excitation lens current, we can easily change the focal length of the lens system. We can change the magnification quickly and with a wide range of the magnification as like this. This is very convenient in transmission microscope. And also, focus length change of the first intermediate lens as objective lens backfocal plane. Here, electron diffraction pattern is generated. First intermediate lens focused on backfocal plane, electron diffraction pattern can be obtained. Then electron diffraction pattern is magnified in the intermediate lens system. Finally, we can project the electron diffraction pattern. We can observe electron diffraction pattern in reciprocal plane, and also real space of the magnification of the magnification mode. We can observe both real space imaging and reciprocal diffraction information simultaneously. Electron microscope is so convenient to observing the space information as like this. As this is just an example of low magnification. Magnification is just a 50 times magnification. We can observe the whole field of view of the grid. Effective area of the grid, 2 millimeter, a metal grid can be observed, and also sectioned sample, biological example is clearly observed. Okay? And also magnified about 10,000 times magnification of the sectioned rat biological example. Small intestine of the rat specimen is microtome slicing and negatively, stained with heavy element. We can clearly observe the microvilli of the intestine, inside of the intestine, and magnified another 10 times of the magnification. We can clearly observe the fine structure of intestine, of microvilli of small intestine as like this. As observing high resolution imaging, even in the biological sample, the microstructure is clearly observed like this. And also, this is an example of high resolution imaging. Specimen was a single crystal of gold, but inside of the gold here, a grain boundary can be observed, and white dot in the image corresponding the single atom location. As interesting as grain boundary here, atomic location, atomic arrangement is misfit as like this. We can clearly each atomic location structure analysis in the crystalline like this. And also, this is an example of electron diffraction. Okay, so specimen was an organic material of L-histidine. L-histidine is very famous as a medicine or food, but a very beam-sensitive material. Then electron dose is reduced. We can obtain the selected area diffraction from small crystalline as like this. Then in even the powder, but small crystalline has a single crystal. We can obtain the single crystal electron diffraction pattern as like this. According to this diffraction pattern analysis, we can identify the crystal structure as like this. Okay, as like this, electron microscope is applicable for wide variety of the field, such as the ceramics, catalysis, carbon material, energy and battery materials, and metals, semiconductors, and biology and medicine, medical science, and also chemicals and polymer science, as like this. Now, I'd like to just introduce the technique of the high resolution imaging. As already introduced, in high resolution imaging, scattered electron is accepted for image forming. Center beam is transmitted electron, scattered electron from the lattice information of the crystal. Due to the scattering angle, so the image forming ray pass due to difference, due to phase contrast, phase shift generated. After that, interference fringe appearing in the image forming system like this. Okay, as this interference fringe distance is equal to the structure of the image as like this, because this scattering angle is corresponding the black reflection. Okay, due to the wavelengths and the spacing, scattering angle determined, and the phase shift is also determined. So finally, we can observe the lattice spacing in the image plane. Okay. In order to perform the high resolution imaging, specimen thickness is very important, should be very thin. Because if specimen is thick, electron generate a multiple scattering. Phase shift become very confusable. The single scattering is expected. We prefer like a very thin sample. And also diffraction information, scattered electrons should be accepted by the big objective aperture. It's very important. Okay, if small aperture applied and scattered electron omitted, we cannot obtain the high resolution imaging. And also, in order to generate the high contrast of interference fringe, suitable under focus is recommended. This is so-called the optimum under focus or Seltzer focus under focus condition. Okay. As like this is just an example of the point resolution measurement. Specimen was applied as amorphous Germanium film because amorphous structure has any kind of structure, high frequency or low frequency, like a white noise generated, and gold particle is the reference for the magnification calibration for lattice spacing. As Fourier transformation of this high resolution imaging, we can observe the spot from the single crystal of gold, such as the 0.23 nanometer for gold lattice spacing. This is for effective to the magnification calibration. And the first dark ring corresponding to the point resolution. In this microscope, point resolution was 0.23 nanometer can be obtained. Ring diameter and the spot diameter of the gold particle is the same distance, meaning the same spacing can be obtained. And this is example high resolution imaging of silicon 110 orientation crystal. Left-handed original high resolution imaging, as simultaneously we can obtain the electron diffraction pattern. Crystal is well aligned the zone axis condition. We can observe the high resolution atomic arrangement inside of the crystal. And also Fourier transformation applied here. Then some of the band pass noise pass filter applied. We can improve the smoothing and high resolution imaging. Image quality improved as like this. And also this example of high resolution imaging for ceramics observation. Specimen was the hexagonal silicon nitride 100 orientation. This is a lower magnification. This small area magnified. We can clearly observe the hexagonal black dot structure as comparing the atomic arrangement model. Green corresponding the silicon atom, red corresponding nitrogen atom location. As silicon is relatively heavy, then we can observe the silicon atom location as a black spot, as like this. Center white is a hole, no atom area. Electron passing through the center holes at a strong intensity like this. Here we can clearly observe the high resolution atomic arrangement structure analysis in high resolution imaging. Now I'd like to shift to the electron diffraction subject. As we are illuminating the electron wave as a parallel beam condition, we can observe the electron diffraction, two-dimensional electron diffraction pattern, and also sometimes we can illuminate the beam convergent beam condition. We can observe the electron disk pattern, convergent beam diffraction pattern. As the electron diffraction pattern principle is exactly the same as a black reflection for X-ray diffraction like this, as lattice spacing with the D-spacing, electron wave is deflected and enhanced with a special angle, incident angle theta and exit angle theta, depending on the D-spacing. Yeah, a strong electron is enhanced in the black reflection condition. Then we can observe the electron diffraction in diffraction mode as intermediate lens, first intermediate lens focusing for back focal plane of the objective lens. As in the considering the electron diffraction pattern, this is a specimen here, objective lens here, this is a back focal plane electron diffraction pattern formed, and this is the image plane of the objective lens here. Okay. In image plane, we can install the selected area aperture, small mechanical aperture install. We can limit the field of view. Then this corresponding area correspond to the specimen position as selected area size as like this. If we apply the 10 micrometer diameter of the aperture, selected area aperture, as objective aperture magnification is 50 times magnification in general, then on the real spacing of the area is going to 200 nanometer diameter on the specimen position as like this. This is the selected area aperture. Area is selected. We can make an electron diffraction pattern, only this small area. But sometimes we are now going to the nanoparticle and catalysis analysis. 200 nanometer order limitation is a too big area. Then now recently we can make a nanobeam diffraction on analytical microscope like this. This is a condenser lens system, first condenser, second, third, and condenser mini lens system, and objective lens here. We can make a small probe of diameter for illuminating sample, such as a 1 nanometer order, or sometimes sub-nanometer order beam possible. Then in this condition, illumination area is limited to beam diameter. Then we can make a small area diffraction. Yeah. This is a semiconductor example, low magnification image. This small area is magnified as right hand here. Here is a amorphous, some silicon oxide area and background, and crystalline can be obtained. Applying the whole area of selected area diffraction, all of the area information is overlapped. But blue line, beam diameter, this is a 10 nanometer scale here. Beam diameter about 5 nanometer beam is selected in the amorphous area. Diffraction pattern go to the hollow, meaning amorphous structure. And the yellow area in the crystal, single crystal with the specimen, we can observe the single crystal diffraction pattern, and red pink area, another orientation of single crystal like this. As selected the nano beam diameter with a 5 nanometer order in this example, we can select the area by the beam position and beam diameter. So nano beam diffraction is very convenient to analyze the local area as according to the field of view. And this electron diffraction pattern analysis can be made by according to the camera lens like this. We can measure the d-spacing from the crystallography of measuring the distance from center to scattered electron spot as like this. If the camera lens is well calibrated, the precision is accuracy is error is less than the 1% order. We can measure the d-spacing by the electron diffraction pattern. Okay. And also condenser lens combined as making the small probe and simultaneously big convergence angle. We can make a convergent beam diffraction as like this. This is a convergent beam diffraction pattern example from silicon 111 orientation. Left hand is the almost parallel. Convergence angle is very small, 0.5 milliradian. We can observe that similar as a selected area diffraction. Middle one is the 4 milliradian beam diameter. So diffraction pattern becomes the disk size as like this. Disk diameter corresponding to the convergence angle. And increasing the convergence angle 15 milliradian like this, disk size is bigger than d-spacing, scattering angle. Then is diffraction spot. Disk is overlapped like this. Then we can observe the coherent information, and also inside of the 3D information of the crystal can be obtained inside of the disk pattern of the CBD pattern. And also simultaneously, higher scattering order, we can clearly observe the Kikuchi pattern as clearly like this. Okay, now I'd like to switch to the analytical electron microscope. Here, I'd like to introduce STEM imaging technique and also analysis, X-ray analysis, EDS, and electron energy loss spectroscopy analysis. First one, STEM imaging. The beam is focused on the sample. This is different from the conventional transmission microscope. Beam is not parallel. Some of the convergence angle is higher, about a 20 milliradian order, but small diameter is being focused like a scanning microscope, and beam is scanned as two-dimensional. It's the same as a scanning microscope. But signal transmitted electron can be obtained. Center beam as a bright field of STEM image, higher scattered electron detected by the annular type detector simultaneously. And also, center beam can be introduced to the electron energy loss spectroscopy analysis simultaneously. Advantage of STEM imaging. Scanning STEM image can be observed by scanning image simultaneously in position is corresponding EDS X-ray analysis, nano analysis, and also electron energy loss spectroscopy analysis simultaneously. So STEM formation is very convenient to apply to the analytical technique like this. Then electron beam is a transmitted electron go to bright field imaging by the bright field detector, and the scattered electron can be detected the annular type dark field imaging. In the scattering angle in higher than 50 milliradian, we call it high angle annular dark field imaging. This is just an example of a STEM bright field image in left hand and right hand dark field imaging. Sample is a heavy element of platinum particle distributed on zeolite crystal. As zeolite is a relatively light element, silicon and oxygen, but platinum is heavy. Heavy element go to dark contrast in bright field imaging. This is similar as a bright field conventional TEM imaging. But dark field of STEM imaging, white contrast corresponding heavy element of platinum, because heavy element scattered electron much higher angle. And also a small particle, as comparing the scale marker, this is a 20 nanometer scale marker, small spot corresponding about 1 nanometer or less. Even the small particle, but we can clearly observe the white contrast clearly, as if this is a dark sky, a star in the dark sky like this. This is why a high-angle dark field STEM imaging is very convenient to observe the heavy element distribution in light element combination. Okay, as recently aberration technology is developed and well distributed and commercial microscope. As upper is a conventional convex lens, a convex lens has the aberration, spherical aberration like this. As the image plane, beam size a little bit broad due to the focal length is depending on the incident angle of the lens system. Then aberration corrector is equivalent like a concave lens like this. But practically in the magnetic lens, round lens system cannot generate. Then hexapole or octapole or dodecapole, multiple aberration corrector is applied in the commercial. Then finally, we can correct the spherical aberration. We can clearly observe the very fine focus on the image plane. Owing to the aberration corrector, STEM resolution drastically improved. Left one is a conventional without aberration corrector STEM imaging, 200 kb. Spherical aberration was 1 millimeter order. Specimen was a Koji crystal of aluminum, copper, cobalt system. We can clearly observe the atomic resolution, but little bit contrast is less and broad. Right one, same sample with STEM aberration corrector. Resolution drastically improved, and white dot corresponding the heavy element of cobalt and copper, and spacing atom to atom distance is 1 angstrom. It's clearly resolved as like this. Owing to the aberration corrector technique, we can clearly observe the STEM atomic resolution in analytical scanning microscope like this. Then current situation of the highest resolution in the STEM condition, applying this 300 kb aberration corrector microscope, grand arm from JR, we can obtain as 40 picometer order resolution. Now STEM resolution is a picometer order, as like this. owing to the aberration corrector technique. Champion data is like this, 33 picometer, 38 or 36 also possible like this. So aberration corrector is improved resolution drastically as like this. Okay, now I'd like to introduce X-ray analysis. As incident electron, as this electron has a much momentum. In the analytical microscope, we never consider electron is a weight. Electron is just momentum. This energy transfer to the atom-electron interaction. Some of the result of the interaction, characteristic X-ray generate. There are many kind of information generate. Then there's many kind of analytical technique. But today time is limited. Only introduce this X-ray analysis as like this. Okay, as electron beam focus small diameter on the sample, then electron excited. Then as electron become vacant due to the excitation, another higher position of electron is dropped down. This energy difference can be transferred to the characteristic X-ray. This X-ray is detected by solid state X-ray detector. Okay? The silicon drift detector is recently developed. Detector only cooled with a Peltier cooler system. No leaking nitrogen now necessary. And X-ray was analyzed by the multi-channel analyzer, X-ray energy, and also photon, X-ray photon intensity is counted simultaneously. We can make a different X-ray photon energy and photon intensity makes X-ray spectrum as simultaneously. As practical configuration in the specimen chamber, here the specimen here, upper pole piece, lower pole piece, X-ray detector, recently windowless detector developed, is close to the sample. X-ray is collected by X-ray detector here like this. Then, as in the transmission microscope, the analytical station a little bit different from the scanning microscope or electron probe analyzer. Because scanning microscope and electron probe analyzer applied a very thick bulk sample. Even the small probe of electron incident, but X-ray generation is diffused and generated diameter almost 1 micrometer order area. So X-ray analysis spatial resolution is limited as minimum 1 micrometer order in scanning microscope or electron probe microscope. But in the transmission microscope, specimen is very thin. Thinner is better. As mentioned before, less than 100 nanometer or 200 nanometer, suitable thickness about 50 to 60 nanometer order. Then electron beam is very small. There is no volume to diffusing the X-ray generation. Then spatial resolution of X-ray analysis is almost depending only the incident electron beam as like this. We can have a very high spatial resolution, nanometer order or angstrom order, spatial resolution of X-ray analysis now possible. Then as like this, as small diameter of the probe, irradiation, boron nitride particle, boron nitride supported by the carbon film, light one, the X-ray spectrum. We can obtain boron K signal, carbon K from the background support film, nitrogen peak, and oxygen peak is the absorption gas from oxygen gas, absorption on the carbon film. As like this, even the light element in the neighboring element, boron, carbon, nitrogen, oxygen, clearly resolved and well detected as like this. X-ray analysis is very convenient to make elemental distribution and combination scanning image, scanning transmission microscope, STEM imaging, simultaneously we can select the characteristic X-ray energy. We can make elemental mapping as like this. And current station of combination aberration corrected STEM imaging. This example of grand arm 300 kV aberration corrector microscope specimen was a silicon oxide crystal. Here is a grain boundary of silicon oxide crystal white dot corresponding heavy element of the zircon atom arrangement, but a dopant, low concentration of dopant yttrium atom is segregated on the interface as yttrium element, characteristics X-ray mapping here as green, and also oxygen and zircon, oxygen red, zircon blue, RGB reconstructed. We can clearly observe the zircon oxide and also yttrium segregated atomic position at the single atom resolution condition. This is now the performance of aberration corrected analytical electron microscope. We can clearly observe the single atom location in elemental distribution condition. Now, next subject, electron energy loss spectroscopy. As specimen should be very thin, transmitted electron, and elastically scattered and inelastically scattered electron is generated. These transmitted electron can be analyzed by the spectrometer. Mainly, the inelastically scattered electron has the information from the chemical information from sample. The feature of the ELUS is energy range for analysis is 0.3 keV order and energy resolution 0.1 to 1 eV order. Resolution is very high. We can observe the chemical bonding state. And also, this analysis technique has a higher sensitivity for lower light element system. As magnetic spectrometer is applied, this sector-type magnet is installed as a lower than the bottom of the column, so we call the post-column spectrometer. In the spectrometer, in the uniform magnetic flux applied, electron beam generate a round motion as Lorentz force. The radius of this bending is depending on electron energy. Higher energy of transmitted electron, bigger radius, scattered and energy loss electron, inelastically scattered electron has a smaller angle. Then we can make an energy loss spectrum at the image formation position. We can make an energy loss value and electron intensity by CMOS camera counting system. Then we can measure the energy loss spectrum, the horizontal energy loss value, 0 meaning absolutely 200 kV in the 200 kV machine. This is a strong sharp peak is a zero speed. And plasmon excitation, intensity reducing by the exponential law, but sensitivity of detector is magnified, about 1,000 times magnification. The background is coming, also boron K signal and nitrogen K signal can be detected. The sample was boron nitride here. Then removing the background here, we can select the net intensity of background K and nitrogen K signal as like this. Okay. Then, as combination with aberration corrected STEM imaging, we can observe the atomic resolution STEM imaging simultaneously electron energy loss spectroscopy applied. Then energy filter applied, such as strontium. Sample was the strontium titanate, strontium M peak, and titanium L peak, and oxygen K peak, and also background subtracted. Net elemental signal is plotted and color mapping image, strontium M mapping. We can observe the atomic resolution elemental information, and titanium L atomic resolution, and also oxygen column here. RGB reconstructed here. Red is a strontium atom location. Blue, meaning green and blue is light blue corresponding, green and green corresponding, because titanium oxygen overlap in the crystal like this. As a crystal model is here, inside here is a octahedron structure. Center is a titanium, upper bottom oxygen located. And four corner, single atom oxygen located here. We can observe the blue of the atomic location as like this. As atomic resolution condition, we can observe the elemental information clearly. This is the current status of aberration corrected ELUS elemental analysis like this. And also owing to the higher energy resolution of ELUS, we can observe not only the elemental information, but also chemical bonding state. This is just an example of the carbon. Left one is a diamond, silicon structure of diamond. Right one is a graphite, layer structure like this. Energy loss spectrum from the carbon material. First one is amorphous carbon. Okay? Carbon-carbon bonding, very loose. Then a carbon K peak, small pi sigma, very loose and broad. But graphite, here the strong carbon pi peak and the sigma peak like this. But from diamond, there is a no pi bonding, only sharp sigma peak can be obtained, and peak shape of the sigma peak from diamond, a big difference as like this. This is our fingerprint of carbon material. As observing the ELS, high resolution fine structure analysis, we can identify the carbon bonding state as like this. Okay, ELS is very convenient for analyze not only the elemental information, but also this chemical bonding state. Okay, now time is limited. And so here I'd like to summarize the transmission microscope here. Okay, transmission microscope, STEM, both offer the very high resolution imaging, atomic order, or sub-angstrom. Now, owing to the aberration collector technology, resolution is arriving picometer order, and we can clearly observe this high resolution in the real space imaging. And also this TEM and STEM can offer the electron diffraction. The information is the reciprocal information. Okay? And also the diffraction is from small local area, nanometer order or sub-nanometer order area diffraction possible. So this is very effective. We can observe the very small single crystal diffraction analysis. We call this nanobeam diffraction, like this. The microscope can offer real space information, reciprocal information simultaneously with one machine. And also analytical scanning microscope can offer elemental information from the sample, and also it's a very small local information, and also combination with electron energy loss spectroscopy, we can measure the chemical bonding state with nanometer area, atomic resolution like this. This is the most advantage of electron microscope. As introduced today, electron microscope is very effective and powerful tool for material science and also biological analysis structure. So I'd like to recommend and I'd like to expect to use the electron microscope in your research work. Okay, thank you very much for your attention.
Thank you, sir, for an informative talk. We have certain questions lined up for you. And the first question is, can degree of twist be determined for chiral structures like DNA using TEM?
Yes. Okay. So yeah, DNA has a structure like a kind of a crystal. It's a biological, but like a crystal. Then we can apply the nanobeam diffraction. Okay. So technically possible, but many important technique necessary because this kind of biological crystal or DNA molecule are very beam sensitive. If we irradiate the specimen by the strong beam, specimen easily broken. In order to keep the structure, we have to reduce the irradiation intensity, very low electron dose condition, and simultaneously we apply the crystal to frozen sample. Because room temperature, the crystal is very flexible and very soft material, structure easily changing. Then we can make a rapid freezing technique, and the sample is frozen in amorphous ice. Then cooling the liquid nitrogen temperature condition, specimen is relatively stable, like a material. Then combine the low dose illumination, and we can make a small area nanobeam cryo nanobeam electron diffraction. And also combination with analyze the diffraction, different kind of direction, because electron diffraction offered only two-dimensional information. In order to observe the three-dimensional information reconstruction, we need a different orientation of analysis necessary. Then we can try to the many kind of crystal, because the sample of the in embedded dice is the direction is random. Then we can collect the many nanobeam diffraction from the many kind of sample. Then this is equivalent to observe the different orientation diffraction collection. After that, this information is reconstructed, okay, as accumulating reconstruction. Finally, we can realize the crystal structure, 3D structure of the sample. This is a very latest technology, but now we can perform this very interesting technique.
Yeah.
Okay,
So,
it's a very good question. Thank you.
thank you, sir. So, what are the softwares available to index the diffraction pattern?
Yes, possible. We can reconstruct the structure as comparing the crystal model. We can clearly identify the d-spacing and also mirror index and the structure analysis. We can determine the 3D structure information from this reconstructed diffraction.
So, as mentioned, HRTM can be used for biological sample analysis. Is it useful for the analysis of an emulsion with higher water content?
Pardon, water included sample?
Emulsion.
Emulsion. Okay, yeah, possible. And because as emulsion is a kind of liquid, so not a solid. In order to analyze, sample should be stable, because if atom is flexible, emulsion looks amorphous. Then in order to make a structure analysis, we have to fix the structure. Then sample should be frozen, rapidly frozen, same as a biological crystal. Then the structure is fixed in the liquid nitrogen temperature. Then we can make analysis like a solid material.
Sir,
Possible.
at what resolution can we see the framework of zeolite?
Resolution is determined, but the original microscope resolution is very high, but it is due to the very strong electron dose, good SN ratio. But also emulsion or biological structure is very beam sensitive. We have to reduce the electron dose as less as beam damage less. Then resolution is limited, this SN ratio of the detected signal. Okay, so if increase the intensity, SN ratio increase, but electron damage happen. And sometimes less dose, no damage, but less SN ratio. So this is the balance of the intensity of SN ratio. Okay, so a little bit bigger distance is more easier to analyze. Okay, so now analysis resolution is limited depending on the intensity of SN ratio of the signal. This is a practical situation.
Yeah, thank you, sir. Sir, another question is, can degree of turbostatic carbon present in the sample be quantified? Carbon.
Sorry?
Can degree of turbostatic carbon present
Degree
in the
of
sample?
carbon.
Yes.
What is the degree of carbon? Have the definition and bonding structure or something?
Quantification.
Quantification. Okay. Carbon concentration. Yeah, in this condition, EDS analysis, we can make a carbon signal very clearly, and simultaneously we can observe another reference signal. We can make a quantification calculation. So we can clearly analyze the carbon concentration or another elemental concentration by quantification of EDS is recommended.
Apart from this, we have questions regarding yields analysis. Sir, kindly comment on element quantification, which is obtained by STEM EDS versus yields technique.
Okay.
As mostly STEM EDS quantification data
Mm.
is presented in research papers.
It's a very good question. The EDS analysis is recommended for quantification because X-ray is not so strong absorption in the sample. Okay? But ELS has a plural scattering or multiple scattering in the sample. Then quantification information very confused. Then precision, accuracy is less in the ELS analysis. Then if the purpose or target of the quantification of concentration, the EDS analysis is recommended. Okay. ELS prefer not the quantification. Quantification theoretically possible, but prefer we recommend the chemical analysis because owing to the higher energy resolution. So EDS ELS is a different tool, different target.
So the next question is, usually each spectrum has high noise, so it becomes difficult to get the signal peak even after background subtraction.
Mm. But after background subtraction, we can make a quantification possible. But this background intensity strongly depends on the specimen thickness. Then if sample specimen in the thick condition, background intensity very big. Then quantification precision, quantification accuracy become very less. Okay, so EDS analysis is recommended because the background of EDS is very less. Okay.
Thank you, sir,
Right.
for
Thank
answering
you.
all our questions. On behalf of SAF CRNTS IIT Bombay, we would like to thank Dr. Oikawa for such an interesting talk. We would also like to thank our HOD, Professor Suparna Mukherjee, and GEOL team for their support in conducting this webinar. Last but not the least, we thank all the participants for attending this webinar and making this event successful. Thank you.
Thank you.